I have the impression that a lot of people here don't work on an axion, so I will first go over some of the theories and the motivations and the more traditional kind of axion detection, and that will motivate this dielectric haloscope concept. And then I will talk about some of the difficulties, the challenges that we have in making this experiment a reality. So when we talk about axion, we have to talk about the strong CP problem. So we know that in the standard model Lagrangian, we have this term in the QCD sector, and this sector contains a CP violating term where theta should be a parameter on the order of 1, and it has two contributions from QCD and from the electroweak sector. So if the theta parameter is not non-zero, then we should be able to measure non-zero neutron electric dipole moment. But decades of experiments on neutron EDM have found out that theta is extremely small. This is particularly problematic compared to other fine-tuning problem in that theta has two very distinctive, very different contributions, and they shouldn't know about each other. To answer this question, Roberto Peccei and Helen-Quinn came up with this, what we call Peccei-Quinn mechanism, where they introduce a new global U1 symmetry that spontaneously breaks at a very high temperature very early on in the universe. And the axion at this time is this pseudo-Goldstone boson. And as the universe expands and the temperature continues to drop, and as we approach the QCD phase transition temperature, suddenly this Mexican head potential is tilted so that the axion starts to roll down. And as the universe continues to cool down, then this axion field becomes a tiny residual oscillation at the bottom of this potential well. Hence, we can make this theta very, very small dynamically. And it turns out that the axions produced by this misalignment mechanism are very cold, as in they're non-relativistic, so they can be a very good cold dark matter candidate. The natural question to ask is, what is the mass of the axion? So if the axions exist, they will participate in lots of processes in stellar objects. So they can contribute to the cooling of stars, etc. And from that, we can exclude a lot of the phase space in the axion mass. If we assume that the axions make up all of the cold dark matter in the universe, this is roughly the region where the axion mass would be. Of course, the precise prediction depends on the sequence of two critical cosmological events, namely Peccei-Quinn symmetry breaking and inflation. So if the symmetry breaking had happened before inflation, then we live in one of these little patches where the number represents the initial Peccei-Quinn symmetry breaking angle. And then, as the universe expands, we still live in this this little patch. And the second scenario is that the symmetry breaking happened after inflation. In this case, you have to consider sort of a statistical average of these initial symmetry breaking angles, and that gives you a tighter constraint on this axion mass. In any case, so this is the sort of the typical mass range that we're talking about. And for scenario B, which is what we're particularly interested in, we normally use 100 micro eV as the benchmark axion mass. So depends on the specific recipes of the model, axions can have different interactions with different particles, but in general, they always have this coupling to two photons, where the coupling constant is Ga gamma, and you can parameterize it as a unit 1 parameter divided by this Peccei-Quinn symmetry breaking scale. And since we're talking about the haloscope, which means we're trying to detect the axions that make up the local galactic dark matter halo. And now I'm going to make the argument that these axions behave, you can consider these axions to behave more like a classical wave rather than your typical particles. This is because for axions of mass around 100 micro eV, and we consider this local dark matter density, you can calculate that the axion de Broglie wavelength is on the order of tens of meters, and the axion phase space occupancy is extremely high. This means that you can think of them as like a coherent classical wave. And just like the other cavity haloscopes, we use this inverse Primakov effect, where we replace one of the photons in the axion to two photon coupling with a virtual photon provided by a strong magnetic field. And in this case, we can consider this macroscopic Axion-Maxwell equation under an external B field as such. So this is sort of the not so up-to-date status of the search for axion to two photon coupling. So this band here is the QCD axion model band, where the KSVZ model has a larger coupling constant than the DFSZ model, and you can see that only ADMX has been able to reach down to the QCD line so far. And this range is the mass range predicted by the post-inflationary scenario. And as you can see that this space is still very empty, and this is what we're interested in. Right, if we look at this set of equations, and because if we consider an experimental apparatus that is much smaller than the de Broglie wavelength, we can safely ignore these two terms. Then what you're left with is this equation. So what this means is that in the presence of an axion field and a homogeneous B field, the axion field can source a static electric field, which is proportional to the axion to two photon coupling, and also to, it depends on the dielectric constant. So this field, if you calculate the amplitude, you get something on the order of 10 to the minus 12 volt per meter. This is extremely small. So typically what we do is that we can couple this static axion-induced electric field to a cavity such that you get an enhancement of the axion signal. So how much of the axion signal is boosted depends on the relative where the frequency is relative to your cavity line width. So this is the typical power that you get for an ADMX type axion haloscope, where you search for an axion where the photon that you produce is on the order of half a gigahertz. And the signal that this kind of detectors measure is mostly noise. So the noise comes from two parts. One is that you have these resistive losses in your material, so that gives you the thermal noise, and the receiver itself would also have noise that will contribute to the spectrum that you measure eventually. So we just lump everything together and characterize it as a system noise temperature. And if you calculate the noise power within the axion bandwidth, you get something usually many orders of magnitude larger than your axion signal. So the way that we detect this is that you integrate for a long time, so that you can reduce the uncertainty of your noise spectrum to such an extent that your small signal would appear after some time. And the figure of merit for such an experiment is the so-called scan rate. So that tells you how much frequency space you can cover for a certain amount of time. Sorry, I forgot to mention that, of course, because we don't know where the axion mass is, we have to be able to scan over the frequency by, in this case, by changing the position of a tuning rod inside of a cavity haloscope. So there are lots of reasons why the cavity haloscopes have difficulties going to higher frequency. So here I'm showing you the typical signal power for two very successful haloscope experiments, ADMX and HAYSTAC. So as you can see, they're focused on different axion mass ranges. And if you put in the typical parameters for the cavity volume and the Q factor, etc., and this is the kind of signal power that you would get. And it's pretty obvious that, you know, once you go to higher frequency and higher axion mass, you get a much smaller signal. This is not the fault of the experiment. So you cannot really increase the volume times cavity form factor because that's scaled by the Compton wavelength. And the Q factor also decreases for higher frequency if you stick with the copper cavities. And increasing the B field is very, very costly. And of course, you can also try to lower the system noise temperature, but it has a limit imposed by quantum physics. Of course, there are ways to get around that, and HAYSTAC has done that successfully. But this is not an easy task. So this makes you think that perhaps new detector concept is needed for higher frequency searches. And so dielectric haloscope is one of these concepts. So if we go back to the drawing board and look at this set of equations, one thing to notice is that this axion modified Maxwell equation also does not allow discontinuity of the E field parallel to the dielectric boundary, which means that if you indeed have a discontinuity in the epsilon, you would have a discontinuity in the axion sourced static electric field. And in order to compensate for this discontinuity, you have to have two electromagnetic waves radiated out from this surface to compensate for that, so that you don't have this discontinuity anymore. And the amplitude are related to the dielectric constants of the two medium. So, of course, the signal power is still extremely small for the radiated wave. But you can imagine that if you have a lot of these interfaces, you can get an enhancement of this radiated power. So indeed, we can do this exercise to calculate it. So here I'm just showing you these formulae. You don't have to go into this, but it's just to show you that there's a way of calculating this, at least theoretically, where all you have to consider is this continuity condition at each boundary. And you can calculate everything in this kind of matrix, transfer matrix formalism. If we put a perfect mirror on one side, and there are two important parameters that we have to look at. One is the reflectivity, which is how much, if you send in the wave from one side, how much you get out from this side, from the same side, and the amplitude boost. So this is the sort of the amplitude boost relative to the case where you just have one mirror here, and none of these interfaces. Of course, to do a real experiment, and you want to have frequency tunability, it's not easy to use to just have materials with different epsilons. So what you can do is to have disks, so that you have a vacuum, epsilon larger than 1, a vacuum, and etc. So if you place these disks in the right position, you can get a power enhancement for certain frequencies. So there are two effects that can actually contribute to this power enhancement. One is that you have coherent and in-phase emission from each of the interfaces. And then for each of these radiated waves, you can have resonance effects within this mirror plus disk system. So which means if we can get a power boost factor of about 10,000, then we can boost this signal power to a level detectable by a state-of-the-art amplifier. And of course, this whole thing has to be in cryogenic temperature to lower the system noise temperature. There are two really great properties of the boost factor. One is what we call the area law. So if you integrate the power boost factor over the entire frequency range, you get a constant roughly proportional to the number of disks. This means that we have the option of doing a broadband scan for discovery and narrowband scan for measurement. And this plot shows you the tunability and the sort of the stability of the boost factor. So the color shows you that frequency tuning can be achieved by changing the disk positions, and this envelope here is obtained by randomly varying the disk positions by 15 micrometers, so that to show you that the boost factor is still stable with small systematic uncertainties. So we did the calculation, and we found that in order to detect QCD axion, what we need is something with the interface on the order of 1 square meters and a magnetic field about 10 Tesla, and we need about 80 disks. In this case, we can achieve a beta squared on the order of 100,000. And contrary to the cavity experiments, our integration time, so scanning speed per channel, is on the order of days rather than minutes. So yeah, this is kind of our best scenario design, where we would have 80 lanthanum aluminate disks, each with 1 millimeter in thickness and 1 square meter in area. And the dipole superconducting magnet would have a large warm bore and very high homogeneity. So before I move on, I just want to show this comparison. So the important thing to point out is that our frequency range, our target frequency range is a decade higher than the typical haloscopes, and our operating temperature is at 4 Kelvin rather than the typical dilution fridge temperature that, for example, HAYSTAC operates in. And our integration time is on the order of days rather than minutes. And as I will show you later, that this experiment is highly complex. So if something sounds like too good to be true, it's probably too good to be true. So this is something that we're still struggling with in a way. So in the remainder of the talk, I will show you some of the biggest challenges for MADMAX, which is that the boost factor is not a measurable quantity, unlike in the cavity haloscope, where you can just do a reflectivity measurement to get the coupling and transmission measurement to get the Q factor. So that's not something that we can easily do. So the strategy for us is to estimate the boost factor using a model, and then we have to constrain the model by other measurable quantities such as the reflectivity and the noise. I will also show you that we have developed a frequency tuning procedure to mitigate some of the limitations from modeling. And an important caveat is that this is very much a work in progress. And I will also show you some progress we made in terms of simulation of the 3D effects that can have a significant impact on the boost factor. And I'll show you our current receiver chain that allows us to detect a signal on the order of 10 to the minus 22 watt at 4 Kelvin. And I'm sure that you'll probably be screaming about, you know, things like how can you build such a large bore and high field dipole magnet, etc. Then I will show you some of the engineering challenges that we have. So I'll go in a little bit of chronological order now. So the first setup, one of the first setups we have at the Institute is this what we call proof of principle setup, where we have a small booster with up to 20 sapphire disks, each of 20 centimeter in diameter. And you can see this copper mirror at the end. And here we have a focusing mirror and a antenna. So this is what the setup looks like in reality. And recently we have an upgraded horn antenna and focusing mirror system. So like I said, the boost factor isn't something that we can measure, but in a, you know, when we do the measurement, we need to know where the boost factor is. Luckily, there's a quantity that is highly correlated with the boost factor, that is the group delay, which is just a derivative of the phase of the reflectivity. And this is because, as you can imagine, that in this frequencies where the system undergoes a large resonance, you have a rapidly changing phase so that you can have a peak in this reflectivity. So this plot shows you just that. So yeah, this dashed line is the is the group delay, and the red line is the boost factor. So the frequency tuning procedure is as follows. So first, we calculate the group delay with the same disk configurations that would give us the desired boost factor. And then in the real setup, we move the disks iteratively until the measurement matches that of the calculation. So it kind of goes the other way around, as you might be used to. And there's a lot of advantages of this measurement guided tuning procedure. So in this case, we don't really know the absolute disk positions. So we need to understand this disk position from this RF measurement. And of course, there are lots of discrepancies between the simulation and the measurement that we don't know yet. And so this procedure can help mitigate some of the impacts of the inaccuracies. So this is an example of the result where the group delay is shown by this dashed blue line. Sorry, so the simulation, so the dashed blue line shows you the simulated group delay compared to the measured group delay shown in red. And here you also have this boost factor overlaid. And yeah, and the caveat here is that the boost factor is calculated only using a 1D model with some ad hoc parameters that we included. And so this plot shows you the degeneracy between the disk spacings. So this is the case where we only have 2 disks, so therefore 2 disk spacings. This is the result from us doing this frequency tuning procedure many times. And as a result of this disk spacing degeneracy, we also have an increased systematic uncertainty in the measured boost factor. So using this method, we can achieve frequency tuning up to 5 disks. And because of like I said, the degeneracy of the disk spacing, we have systematic uncertainties in the boost factor, but at least, when we go to up to 5 disks, it's still a tolerable systematic uncertainty. However, when we try to go to more disks or more resonant setup, we have some difficulties with this procedure. So there are 2 reasons for this. One is the non-negligible 3D effects, and the other is the higher order reflections from the antenna. So in order to understand the 3D effects, we, on one hand, we used your commercial finite element simulation softwares such as COMSOL, where we can include the axion term as an external current density. We also have developed some custom codes using the ray tracing method and the mode matching method to calculate the boost factor and reflectivity. So this is an example of a calculated boost factor using a 1D model compared to a 3D model. So here the color shows you sort of the molding effect that can happen within the booster. So each of these modes can have a different transverse momentum and therefore different propagation constant along the longitudinal direction. That's why they are kind of separated in the frequency domain. And so using this custom code, we also did studies on the impact of imperfect disks. For example, in reality, the disk can have certain tilts and thickness variations and surface roughnesses, and all of them can have a negative impact on the boost factor. So from this study, we concluded that we have to be able to control the disk tilting to within 100 micrometer for 30 centimeter disks. And the disk thickness variation has to be at least less than 10 micrometers, which is very, very challenging for us. And also, so all these imperfect, imperfections can also change the axion signal shape, which is problematic because we have to sort of receive the signal by a horn antenna, which is typically a Gaussian antenna. And to calculate how much power you can actually extract, you have to calculate the sort of the overlap between this Gaussian shape and your axion beam shape, which will give you another power reduction, as shown by this blue line. And another problem we face is that the signal that comes out of the would-be axion signal that comes out of the booster can also be partially reflected back into the booster. So unlike in radio astronomy, you just look at some object very far away, and even if you have reflection, it does not come back. However, for us, everything is enclosed and the antenna is relatively close to the booster, so you can have all of these secondary and tertiary reflections. So this is indeed what we saw in the measurement, where this is a reflectivity in the time domain, where you can see that this part corresponds to the first time that the signal gets reflected back, and this is the second time, and etc. So we have a way of factoring these in at the moment, where we can apply some time gates, for example, to calibrate out the antenna efficiency and the secondary reflection. But clearly, more sophisticated antenna modeling is needed if we go to more and more disks. And right, so now I'm going to switch gear and talk about the system noise temperature. This is another way in which dielectric haloscope can be very different from cavity haloscopes. Now remember that in our measurement, we care about this signal to noise ratio, where your noise is characterized by the system noise temperature. So for us, this has 2 parts. One is the booster thermal noise, which is kind of a gray body radiation coming out of the booster. And we also have a receiver noise temperature, which is the input noise of the amplifier filtered by the booster and get reflected back. So in order to study this system noise temperature, we built this small setup in the lab where, unlike the previous setup that I showed you, we placed this tiny booster section inside of a metal tube. So it's entirely enclosed. And instead of using a focusing mirror and the antenna, we try to detect the signal with the taper. And the disk spacings are just fixed by these metal rings so that we know precisely what the disk spacings are, and it's more repeatable. And this system is designed to have a resonance frequency at around 19 gigahertz. So this shows you a simulation that we have for the reflectivity and the power boost factor in the case where we do the simulation without the taper and with the taper. So as you can see that the taper slightly shifted the resonance frequency because it's not a perfect impedance match, but for our purposes, it's okay. And another thing I want to mention is the sort of the difference between the open and closed booster, and also the reason why we use the closed booster for the noise temperature simulation study. The main reason is that the open booster has these radiative losses from the side. So whereas for a closed booster, there is no radiated loss. So all the losses are dissipative. So that will allow us to study the system noise temperature. And of course, yeah, you would also have more losses would also reduce your boost factor and also the losses in your reflectivity measurement. So we have this set up for a few months now, and there are still lots of small problems to fix with it. But this is the latest that we have for the reflectivity measurement. So blue is the amplitude of the reflectivity, and the orange is the group delay of the reflectivity, and measurement on the top and simulation on the bottom. So as you can see that we still have a much higher loss in the measurement compared to the simulation, which is perhaps, yeah, not surprising. But on the upside, the group delay in the simulation matches that of the measurement very well, which means we have a relatively good understanding of the system. And so only this peak here is what we're interested in. So this is our sort of design resonance frequency. And all the other things come from mostly the higher modes that the taper created, and that can also have resonance effect inside of the system. So we have developed a noise model to calculate the system noise temperature, where this taper itself is modeled by an n-port S parameter calculated from a finite element simulation. So here I'm only showing you 11 ports where each port corresponds to a waveguide mode on this side. So we have now we have up to TE19 and TM19 modes. And the booster section can be modeled by using the waveguide model, where each vacuum section and disk section can be parameterized by an impedance, characteristic impedance, and propagation constant and attenuation. And of course, you have to build this model for each of the waveguide mode. And as for the noise amplifier, we model it as a noiseless two-port with a correlated voltage and current noise sources. And so the S parameters of this two-port, as well as the noise sources and their correlation, can be obtained from measurements. So here I show you the simulated system noise temperature with an ideal amplifier with a noise temperature, 180 Kelvin at room temperature. So here the dashed lines are the noise temperatures, and the solid lines are boost factor, and the colors are obtained by changing the distance, so the height of this section by about a quarter of lambda. So as you can see that, contrary to cavity haloscope, where you would normally directly go to an isolator so that you have a flat noise temperature, we would have a frequency-dependent system noise temperature. And we're currently studying whether we can take advantage of this to possibly improve the signal-to-noise ratio by adjusting this distance. But this is still an open question. And so now we have the setup in place and simulation ready to go, and we're in the process of doing more room temperature and cryogenic measurements and compare those with the simulations. And so hopefully in the near future we'll have more to say about, how well we understand the system. And now, so from here on, I will talk. So next I will talk about the receiver chains that we have in order to detect this very tiny signal at 4 Kelvin. So this is the receiver chain that we have. So the signal would first go into a preamp at 4 Kelvin. So this receiver would have a 5 to 6 Kelvin noise temperature, and that's followed by a room temperature IF section where we have 3 heterodyne receivers so that we can mix this 10 to 20 gigahertz signal down to something on the order of 50 megahertz. So we did a, at the end of the receiver chain, we have 4 samplers, each with 50 megahertz in bandwidth. And so we connect them in a daisy chain so that because these amplifiers, these samplers have internal FPGAs that can perform FFT, and by using 4 of them together, we can reduce the dead time from 75% to 1%. And this is a picture of the setup that we used to inject a fake signal into this receiver chain and then try to detect it. So here, you can see that, so this is the power spectrum that we have. And this little bump shows you that we can actually detect this fake axion signal after about 2 days of measurement time. And in the future, we hope to replace the HAMT amplifier with a 2-path, so traveling wave parametric amplifier. So these are quantum limited noise amplifiers that can give you a noise temperature very close to the quantum limit. So this is a device built by one of our collaborators at Institute Neo. You can see that they can achieve a performance very close to the quantum limit. And so initially we consider using JPA, but the problem with JPA is that the bandwidth is even smaller than our boost factor bandwidth. So this device is much better for that purpose because it has a gigahertz bandwidth and a very high 1 dB compression point. And then we also don't need to tune this frequency very frequently. And they're also very optimistic that they can use the same technology and build devices that can work up to 30 gigahertz. But of course, this is the first 10 gigahertz device that they have built. And of course, we will have some difficulty in coupling the 2-path to MADMAX because you have to build a structure that allows you to go from 4K to 100 millikelvin in temperature, but still have, your microwave signal still has to go through. So how this can be done is still under investigation. Yeah, and perhaps the largest cost driver and time driver is the dipole magnet. So we've partnered with CA Suckley and Billfinger No to for the design of this large dipole magnet. So our figure of merit is B squared times A. A is the cross section. So that has to be 100 Tesla square meters squared. And this magnet of this scale has never been built before. In any case, they came up with this plan where you have 9 coils on each side, up and down, and this is the simulated magnetic field in the center. You can see it has a very high homogeneity. So currently, they're in the process of doing a quench test of the mock-up coils. But since the funding is not ready to go, so the project is kind of put on a low flame status, but it's still going forward. In the shorter term, our plan is to build a prototype and operate it in the Mapugo magnet at CERN, which can produce a 1.6 Tesla magnetic field. So the prototype design is ongoing. So this is the sort of a preliminary drawing of the cryostat for the prototype. And here you can see this booster section. So we plan to have 20 lanthanum aluminate disks, each with 30 centimeter in diameter, or this or sapphire. And in this instance, we'll also have a laser interferometer incorporated, so 3 interferometer for each disk, so that will allow us to measure the disk positions and tilting rather precisely. And yeah, so the purpose of the prototype is mainly to function as an R&D test bed, but if the operation is successful, we can use it for hidden photon search and ALP search as well. So this is sort of a, well, not even a timeline because there are still so many question marks at the moment. So the collaboration was formed in 2017, and we're currently still in this prototyping phase where we try to understand the physics of the booster and all these mechanics and all the technical issues. So we hope to be able to build and commission a prototype in 2022, where we can operate at the RF lab at University of Hamburg on the DAISY campus without the magnetic field, or we can operate it at CERN with magnetic field during their beam shutdown. And in the future, once all the funding comes together, we can build this big magnet and the final 1 square meter booster. Then we hope to be able to operate this experiment at DAISY in the DAISY node Heron Hall North, where we can reuse the H1 yoke. So this is my last slide. So I'd like to show you the projected sensitivities. So here you can see 2 shades of blues. So we have, if we take a more if we take the approach that we won't get to the DSVZ, then we can use a narrower bandwidth, but then we have to go aggressively towards the implementing the 2-pass so that we can lower the system noise temperature and reduce the adjustment time. Then we can hope to get down to DSVZ, or alternatively, we can also take the approach where we search in a broader frequency range, and this is the sensitivity for that. And here, So in the cyan color is the sensitivity of the small prototype that I just mentioned, if we can do the measurement at CERN for three months. So this is already below the YAXO projection. Okay, so yeah, thank you for your attention. I'm happy to answer any questions.
Thanks a lot for the really good talk. So I don't see any questions in the chat. If there are questions, please either raise your hand or post it in the chat, or just speak up if you're comfortable that way. I see a lot of claps, so I think people enjoyed your talk.
Thanks.
I have a question.
Yeah, go ahead, Steve.
Yes. So the tuning, you have to move all these. At one point you said it's not tunable, but then later on, of course, you have to tune because you don't know the axion mass. So you have to move all those disks together in just the right way, correct?
Sorry, are you talking? Oh, sorry, I lost the sharing. So are you talking about this setup, which is not tunable?
Well, at one point you just said it wasn't tunable. That was early on in your talk, but clearly that wouldn't work. But eventually this whole thing is going to have to be tunable, and you're going to have a mechanism to move all these disks by just the right amount, correct? And
right. So this setup is tunable.
Okay.
And this setup is not tunable yet.
Yeah.
Yeah, of course, eventually you have to be tunable to be able to do the searches.
And is 4 Kelvin low enough? Because we have to get below 100 millikelvin before we don't have any extra thermal photons around. And your frequencies,
yeah, this is
five
why
times higher. So I would think you'd have to go to quite a bit lower temperature. Otherwise, you're going to be dominated by system noise, thermal noise, I mean.
Yeah, so this is why we have to integrate for days rather than minutes. There are lots of difficulties going to millikelvin temperature for such a large system, and we have talked.
I think I think that there'd be no trouble making something that big cold. Frassati at Leiden has a 1-ton ball that for gravitational waves that he cools down to millikelvin. So I think that in principle you could do it as a question of money and engineering. It's already complicated, but it'd be such a huge boost in signal, I would think it was worth it.
It's not only that the temperature itself, right? Because so currently our plan is to move the disks using piezo motors. But once you go down to that low temperature, the piezo element don't expand and shrink that much anymore. So it's hard to find something that can actually move your disks at that temperature for the distance that we want. And of course, because we're only holding the disks at 3 points, right, the cooling would also be a problem in that case. Yeah, it's at least, from my point of view, it's not so easy to go down to millikelvin temperature, and if we can find ways to not have the boost factor degrade so much, this is actually tolerable. We just have to integrate for a bit longer to see the signal. But then we're more broadband, so we can cover a larger frequency range at once.
Yeah, I just would have, it's just even going down to 1 Kelvin, that would give a factor of 4.
Right.
That's a little bit easier. You just fill the whole thing with liquid helium and pump on it.
That's another thing. So if you pump on it, you can shake the whole thing, and then you can broaden your your bandwidth. So the vibration would be a problem in that case.
Well, it's just, people do these things and there's always solutions to mechanical problems. You have an order of magnitude sitting there in improvement. I'm just saying maybe it's impossible, but there are technical reasons and some can be solved, some can't.
Yeah,
anyway,
so
that's all I wanted to say. So
no, it's a good point. We certainly have thought about it, but as you can see from this plot, I didn't talk about this blue curve. So this is actually the booster only noise temperature plus 100 Kelvin. So this is all room temperature calculation. So the emissivity of the booster itself is actually quite low, which means most of the noise actually comes from the amplifier itself. So if we can find a way to implement this, the 2-part inside, then we can, we can really lower the system noise temperature by quite a lot. But then, of course, the problem is how you can go from 4 Kelvin to 100 millikelvin and have this jump in temperature. And have this jump in temperature and still have the signal transmitted.
Okay. Thanks.
Yeah.
Oh, sorry, go ahead.
No, I just was going to say that, you have a dielectric waveguide. I think that's used quite a bit in these types of things. But anyway, it's very interesting and very impressive talk. I'm not meaning to be critical, but I'm saying looks like there's big factors to be gained if you just get it to be colder, which of course but.
Yeah, we definitely would like to go colder if we can. But yeah, I'm personally not a cryogenic expert, so this is the plan that we have for now, and it could change in the future. Well,
none of us are cryogenic experts. We carry on. I'm just joking. We had to learn it all for HAYSTAC, and that's a big complication whenever you make an experiment fully cryogenic, and the colder you go, the more complicated it gets.
Okay, thanks for the question, Steve. I also see Jay's hand. Jay, do you have a question?
Yeah, thanks, Xiaoyue, for the talk. This may be really a naive question, and I must be missing something. But this is also related to the temperature, system noise temperature. So of course, your signal to noise ratio is inversely proportional to the system noise temperature. But if you go to your sensitivity slides, your broadband search is actually operating at the 8 Kelvin. Is this just the limitation of your detector system, or is there something else that I'm missing here?
Okay, so you mean how we go from 8 Kelvin to 4 Kelvin, or?
I mean, why don't you operate in 4 Kelvins in the broadband as well?
Oh, so 8 Kelvin is what can be achieved now, and 4 Kelvin is, if we can implement the 2-part in the system.
Oh, so it doesn't have anything to do with the broadband or the narrowband?
No, the system noise
incremental.
With the bandwidth refers to the booster bandwidth.
Okay, so if you could achieve 4 Kelvin, you can still do the broadband search with the 4 Kelvin as well.
Yeah, so that corresponds to this line here. So if we have 4 Kelvin, yeah.
Okay. Yeah. Oh, I guess that makes sense.
Yeah, sorry, it's a little too small. So if you want to go deeper, then you have to sit on one channel for a bit longer. So you can go broader or deeper, but then there's also a question of the system noise temperature and the bandwidth.
I see. Okay, that makes sense.
Yeah, sorry, it's
Thanks.
not so clear.
Excellent. I do not. Oh, there is a question. Chiran, do you want to read the question, or I can also read it?
Oh yeah, I was just wondering, like in the first setup, why the focusing mirror is used. You might have talked about this, but and like what is the loss if there's any
Oh,
with using this device?
yeah, the focusing mirror has to be there because so your axion signal that comes out of the booster will be a little divergent. So you need something to refocus it, and in this instance, divert it. So on this frequency range, we don't usually use lenses. So focusing mirror is the usual way to go. The loss, because it doesn't really participate in the resonance, so the loss doesn't contribute much. But however, there is a problem with cross polarization, for example. So the focusing mirror can introduce cross polarization, especially for non-fundamental Gaussian mode. So that could be a problem, but we don't really have an idea of how much of a problem that is at the moment, but it's something we have to study. And of course, if we use the sort of the closed booster system, then, instead of focusing mirror and antenna, we can just use the taper. But of course, the taper has to be more optimized than this very simple one.